Howdy folks, Mr. Reed here, and welcome to One More Question. So what I'm going to be taking a look at today is kind of like a precursor getting ready for powers and roots, which is my next batch of videos that I'm going to do for this particular series. For powers and roots, I need to make sure that everybody's on the same page with how some exponent laws work in a whole number sense. Since once we get into talking about roots, we're going to do reciprocals, so we're going to have all kinds of other rational exponents to deal with. And because of that, we need to make sure that we're on the same page in terms of the whole number stuff. So if you want to work off the rust with some whole number exponents, or you've never seen it before, you're in the right place. So let's get to it. All right, first question is we have a cubed times b squared. I actually have 4 of them up above. 3 of them are actual exponent laws, and the other one is kind of a fake. But I want to make sure that we are aware that just because it has exponents doesn't mean there's a nice way to simplify and put things together. So I put an imposter up there. We'll be sus of it and see how it goes. So a cubed times a squared. Now, I'm going to try to give some sort of justification for each one of these rules as we go through it. So, the long way of writing a cubed times a squared would be a times a times a. I'm going to put a little bracket around it. Doesn't need it, but that's where that first group comes from. Times a times a. Which is the same thing as if there were no brackets there at all, which is a times a times a times a times a. And another way to say a multiplied by itself 5 times is a to the power of 5. So what we can do as kind of a speed up process is note that the number of a's that I have here always corresponds to the exponent that it started with, because it's just the count of the number of multiplied together a's. Again, this is how it works with whole numbers. It's a little dicier when talking about the extended version of how that's going to work, but this is a really good visual representation for most of us if we're just starting to get into these exponent laws. This one's a 2, so there's 2 here. So what do? Well, we add together the amount of a's that we have here and the amount of a's that we have here, because all we're doing is counting them up. 1, 2, 3, 4, 5. Perfect. Okay, so how do we speed up that process? We look at these exponents that we start with and we just add them. So if I were going to say this thing out loud and I was going to generalize it, I might say that if you have some base that's to any whole number power, and then you have that exact same base to a different whole number power, that is the same thing as writing it as that same single base to the 2 powers added together. So we would have a to the n plus m. In this case, it was 3 plus 2, so we got a 5. That will always work generally. Of course, this is only really talking about the whole numbers so far. It does extend, but for the time being, that's all we're dealing with, and that's how we're going to explain it, or how I'm going to explain it. Next up, I'm going to wander over to the C, because I usually go left to right, top to bottom. I don't know why I did them alphabetically that way when I set them up. Doesn't really matter. So we have C cubed all cubed. So when you have a cube that is working on a bracket, so the thing that that cube is written next to, like right next to it, is a bracket. It's actually this bracket here that opens there and closes right where you see the exponent. So what that means is that the cube is applying to the bracket. And since this is a whole number, a 3, we can say that this just means we're going to experience repeated multiplication 3 times of whatever this exponent is touching, which is the bracket. So I'm going to say that this is the same thing as that bracket times that bracket times that bracket. Inside, we'd have c cubed inside of each one of those brackets, because that's what's in it to begin with. So seeing it 3 times over, c cubed times c cubed times c cubed. Now, the first c cubed is c times c times c. And again, the next one is c times c times c. And the last one is c times c times c. So we're going to do the same thing we did last time, because this is still c times c times c, and then 2 brackets written next to each other, still multiplication there. So times c times c times c times c times c times c. So there are 9 c's there, all multiplied together in a single string of c's. So just like last time, we said that whole number multiplication, multiplication of a whole number of these things, same c value. It's the same thing as putting this to a single power representing how many times we've multiplied it all together. So we could say that this is c to the power of 9. Now, how do we come up with that kind of in a slightly different way? So what could we say here to change up this process so I don't have to write this out every time I do it? Well, since what we're doing is taking an amount of c's that we have inside that bracket, which is just a countable 1, 2, 3 because of the exponent here, and then we're tripling the amount of that because the external or the outer power that's right here is telling us multiply together whatever is on the inside that many times, which is another 3 times. So we're multiplying this times however many there are already there. So each group that's made, just like when we talk about multiplication, is made up of the stuff that's inside, and then the number of groups is the number that's outside. This many groups of this, multiplication, straight through. So we can take this number and this number, multiply them together, and that's what gives us our final exponent here. So c to the power of 9 is the same thing as c to the power of 3 times 3. Generally then, if we wanted to say something very similar to the way we did it last time, if I had a c to the power of n, where n was representing any whole number that we could bump into, and m was also representing a different whole number that we could bump into, then it would be true that c to the power of nm, which written next to each other with nothing else in between it, means that we're going to take those two constants or values and multiply them together. So all we do is if we have a base with an exponent written on it raised to another exponent, multiply them together. That's the quick way of simplifying things there. All right, so next up I'm going to go with that b. So we have b to the power of 7 over b to the power of 3. And this is going to, I guess, rely a little bit on dividing monomials that you might have bumped into before. If you haven't really a whole lot, I haven't made a video on this yet, but I thought about doing it because it probably should have been a precursor to some of the stuff I already worked on. I might have talked about it a little bit in one of my videos, but I can't remember which one it is, so I'm not going to link one right now or refer you to one. But I'll talk really loosely about it. So in this case, it is a monomial because it is one term that is all multiplied together. In the numerator, I got to count the right number of b's here, so that is 7. And that's all over b times b times b. Now the way that monomials work is if you have any part of them that is in the numerator and you find that same part in the denominator as well, we can actually fully cancel that out. If you multiply something in the numerator by 2, but you're dividing something in the denominator by 2, then whether it's double up top and down bottom, you can cross them both out, and the ratio is still going to be the same. So what we can do here is say, oh, well, that b is going to cancel out, but so does this b, and so does this b here. And there's nothing else to cancel out with down in the denominator. What that means, once you've canceled everything out, it's not that there's 0 left, it's actually a 1. Because we've divided everything by b top and bottom, b top and bottom, b top and bottom. And each of those divisions actually gives you a 1, not a 0. And when we have multiplication, 1's kind of disappear. And so that's why it appears like there's nothing left there. So because you have a denominator of 1, dividing by 1 is the same thing as not doing anything. So what we're left with is the values that we have up top, which are b times b times b times b, which is b to the power of 4. So again, how are we going to speed up this process and make it so that it's a nice little snappy thing that we can memorize and be very comfortable with where it came from originally, but also be able to use it nice and quickly? So in this case, we are again taking a look at these exponents on the b to the power of 7 and the b to the power of 3. Each time you have a b in the denominator and the numerator at the same time, it cancels out like we said earlier. So every single b that's in one place cancels out with the b's in the other place as long as there's at least 1 in both those locations. If you run out of b's somewhere, you can no longer cancel out, of course. But in this case, we can say 7, take away the 3 because each of those 3 gets canceled. that's what gives us the 4. So generally, we could say that b to the n over b to the m, and of course I put them the other way around alphabetically. It really doesn't matter, but well, it's a little bit on the strange side. And so I'm going to say that that is equal to b to the n minus m, because it is the number of b's multiplied together in the numerator minus the number multiplied together in the denominator. Of course, I haven't said this probably yet, but the letter that's involved here doesn't matter. It doesn't even have to be a letter. This can be all working with number values as the basis, and it still works out the same way. So don't get too caught up by the A, C, and B. Those are just representing that there is some base there that we're working with. So if you're dividing something that has the same base, B in this case, then we can subtract the exponents and get the job done really quickly. The last one that I have is the, I don't know, it's called a red herring, is it? I don't know. It is the one thrown in there for no good reason other than to mess us up. So in this case, I do have the same base. I have a D in both these locations. But this is a D multiplied by itself 3 times, plus a D multiplied by itself 5 times. This does not go together in a way where we add the exponents. We actually saw that adding the exponents comes from when we multiply between the two parts. But if we're adding between the two parts, if you've done factoring of binomials, which may be the case if you're hitting here, the classes that I teach would have seen it first. But if you haven't, then you might want to go back and take a look at why this might be true if you've seen how binomials work. I do have a video for that. But if I take d cubed out of both of these two terms, there's 3 of them in the first term, 5 in the second term, so I can take out d cubed from both. It would leave me with 1 plus d squared. And it might be a little more obvious to you that even though you see the base of d on both of them initially and think, maybe they could go together, you're probably pretty comfortable with the fact that 1 and some power of d are very different. And so you're not going to be able to smush them together into a single term because, well, if the d could represent something that's 2 or 4 or 6 or 8 or whatever. I don't know why I only said even numbers there. 11, 13. It could represent any value, could represent all kinds of different things. So it could be negatives, fractions, whatever. It's going to go together with 1 differently for every different d value. So we can't just assume that we know what it's going to simplify to when we put 1 together with d squared. So we don't. We leave it. Which means that there is a different way to write this, but there's not a way to simplify it into a single exponent. So if you ever see something like that, or a subtraction of 2 of the same base, we don't have a nice tidy way to just go and get it to a single value, or a single term, or a single exponent to represent what's going on there. So it's really important that you feel pretty comfortable with this stuff, especially if you're going to expand it past the idea of whole numbers. So hopefully you found that one helpful. If you did, like, subscribe, and as always, take care, folks.